everybody. So, real quick, Vertica, it's an analytical database, but really you're here to hear Josh speak about the distributed systems and machine learning. So if everybody could just, at the end of it, fill out the survey and pass it to your left, we're going to be doing a raffle for a Raspberry Pi at the end of Josh's talk. And with that, I'll turn it over to Josh.
Thanks, Zach. All right, so first of all, a couple of thoughts on Ben's talk, wherever you are, Ben. It was a great talk. Really enjoyed it. So one, Ben is hoping that I'm an ethical person because he let me put my thumb drive on his Mac over there. And he looks a little bit worried. There you are. He looks a little bit worried when I was putting it on there. I'm ethical. And I'll show you my ethics with talking about real quickly a project I did. So with the state of Idaho, Department of Corrections, I built a recidivism model for them back when I used to work for IBM, SPSS. And in that modeling problem, we talked to them a little bit ahead of time about ethics. So I thought your talk was great, right on cue, because there are some things you don't want to do with recidivism models, some trouble you can get in. And thankfully, they were very open to that. And right away, they said, "Yeah, let's avoid race. Let's avoid some of the other factors that might not be things we want to put into our model." But one interesting thing we did find out about that when we built that model was that one of the highest predictors of not having recidivism, meaning they're going to stay clean after they go back into public, was being married. So IBM was also had eHarmony as a client. And so we're like, perfect, we're going to hook up eHarmony with Department of Corrections. We got this nailed. This is going to work. So to my talk, while I was putting this together, I've been putting this together over a couple of months now. I've given this presentation once before at a conference. It's a little bit evolving as I go. I found it very interesting. Hopefully you will too. But personally for me, it's been interesting to think through the problem of distributed machine learning and the pros and cons of whether you go with a general compute engine that's separated from storage, or whether you go with something that's more tied to storage, whether you go with something that has a lot of flexibility, but takes a long time to set up and to build models in, or whether you go with something that's a quick hitter and has other advantages. So that's a little bit of a preview of what I'm going to be talking about, but I'll get into it in a lot more detail here. But I encourage you to think about what I'm talking about. If you have questions during the middle, great. If not, we'll stop at the end and see if the questions there too. First of all, let me set the stage and make sure we all understand what I mean by distributed machine learning, as we're speaking the same language. Basically, I mean machine learning problems that are way too big for R or Python or SAS or SPSS to handle. Okay, stuff you're gonna run out of memory on R, or it's gonna take you all day long. I remember in grad school, I was doing a the AdaBoost algorithm. I was boosting logistic regression back in grad school and doing a project with that. And I would hit go in R and just go. It was like 10 a.m. and just go home because that thing was not going to finish until the next day. Yeah. Just in building them up. And this was the UC Irvine spam data set. Any of you know some of that UC Irvine data sets they have out there? It wasn't a very big data set. So you can definitely have a lot of problems when you run into a little bit bigger data sizes. And some of these graphs here just say, hey, data is really growing. So what do I mean by machine learning at scale or distributed? So in my thoughts today, I really narrow down my assessment of the distributed machine learning space to those that one, distribute across several nodes. So it can't be a single node install. It has to run on several computers at one time. Sometimes people call that MPP environments. They have different math. So believe it or not, you probably would believe it, there's a little bit of different math when you have to split up, let's say, a linear regression or a random forest or whatever, across several computers. And the data is separate on each of those computers, but you still want one model for all the data at the end. So if you're familiar with the Hadoop idea of map and reduce, you have to think about the reduce step when you're doing this. But you can't use map reduce because it's way too slow. You got to go with something faster. And so I looked at, in the distributed machine learning space, who has pre-built machine learning functions, not just a dev environment, for this machine learning on many computers at one time at scale. And at scale, I'm kind of thinking more than 1 billion rows, more than 100 or so columns. That's kind of where I think the line is drawn nowadays, because laptops and just servers are getting bigger and bigger. So you can do more and more with R and SAS and SPSS on single nodes. But once you get to about 1 billion, that's when things start to get, you start to get those out-of-memory errors and such. Okay. So, pop quiz, which of these, this is one of the popular analyst reviews of the machine learning space, which of these products are distributed? Don't, just answer to yourself. Just think about it for a second. And oh, by the way, my disclaimer, this is all according to my research, okay? So this isn't gospel of the machine learning Bible. This is what I found in my experience, and I should probably preface that with what is my experience. I forgot to do the what about me slide. So I've been practicing now for 17 years as a data science practitioner. With Vertica, I am a senior data scientist, and I meet with customers all over the world and help them with different projects in machine learning. I've worked for a couple different companies, IBM being one of them in the past. So, which of these have I found to be distributed? Here's the list, and only 2 of those up there are actually distributed. So usually when the H2O and Microsoft purchased Revolution Analytics a little while. So how many of you have heard of Spark? Okay, so I figured, how many of you use Spark? Okay, that's about what I figured. H2O? Okay, so H2O is very similar to Spark. It's distributed machine learning, open source. They really use their R and R API, so everything's kind of through their R language. So it's a very good alternative to Spark. Revolution Analytics is also started out as R-based. They were a company that said, hey, R kind of sucks on a single node. It needs to run faster for big data problems. Let's re-engineer this thing to run distributed. So they did that, and Microsoft bought them. And then you got 3 that are a little bit different. So I'm going to talk about the differences between these 3 and these 3 in a second. But you got Vertica, you got something called Madlib, and you got something called fuzzy logics. Have any of you guys heard of, who's heard of Madlib or fuzzy logics? Okay, 2, yeah. Usually, oh, 5, all right. That's usually what we get. Nobody's heard of this stuff, right? And so it's a little bit of a public service announcement today is, what the heck is this stuff? Because everybody's heard of this stuff, what the heck is this? So Madlib is a distributed machine learning library that came out of Berkeley, and it's meant to run inside of a database. And so the Green Plum columnar analytic database was the one that's really made that popular. They grabbed onto Madlib. Fuzzy Logic's the same thing. It didn't come out of Berkeley, it came out of a private company, and Netezza is the database that kind of grabbed onto that. That's their in-database machine learning, and they made Fuzzy Logic's popular. Vertica, the company I work for, is developing their own, has been developing it for some time. Vertica is not a huge company, and we have 30 people working on in-database distributed machine learning, so it's a pretty big portion of our dev budget is going to machine learning. We think it's pretty important for the future. So, like I said, breaking these up into 2 camps. I'm going to call these the compute engines, CE. So it's distributed analytic compute engines. They're compute engines because they aren't tied to an underlying data store, right? Most of you guys are familiar with Spark. You know it can run on Amazon, it can run on Hadoop, it can run on your laptop, it can run on a server, it can run wherever. So these can run wherever. And these 3 over here are tied to a database. So they're tied to a data store. And there are pros and cons of doing your distributed machine learning in a database versus a general compute engine. Pros and cons either way. So we're going to talk a little bit about those pros and cons. First of all, what is Spark? Most of you are familiar with it, but for those of you that aren't, here's a couple of kind of architecture slides-ish, architecture slides for Spark. Spark usually is associated with Hadoop. So it does very well at reading Hadoop data sources. It can hook up to things like Tableau and MicroStrategy. It has really nice IDEs for data scientists. So you can program in Java, Scala, Python. You can even do some SQL now inside of Spark. Not everything is in their SQL, but some things are. And they have really nice tools like Jupyter and Zeppelin and other things that let you organize your work really nicely. Spark has a streaming component, it has machine learning and graph analytics, and I already mentioned Amazon and other things as well that it can run Okay, so here's just a few bullet points on kind of what does Spark have going for it. And, oh, by the way, I'm using Spark as the poster child for the compute engines, and I'm going to use Vertica as the poster child for the data marts. But when I'm saying Spark, when I'm saying Vertica, I'm speaking more broadly. It's kind of that whole space. Right? So H2O and Revolution have similar things going for them. And when I talk about Vertica, Madlib and Fuzzy Logics have similar things going for it too. So Spark is really good at scaling across commodity hardware. You can adapt it to any data storage. This is one of the big ones. It can really work well with lots of different data types, especially Hadoop data types. It does great with that. So you can get really customized with your data prep and your ingest. You can do data visualizations, and you can get really customized with your model building. So this is probably the biggest bullet point here. It has the deepest and widest modeling capabilities out there for in the distributed space. Right? Again, we're talking distributed. R, SAS, they're going to have tons of esoteric algorithms that none of these guys have yet. But these guys are working on problems at large scales that you just can't solve on a single node. So here is the Vertica ecosystem. Hopefully you can see that slide with the background colors there. Vertica is, as Zach mentioned at the beginning, is an analytic database. So if you've ever worked with something like Oracle or DB2 or MySQL or SQL Server, to the end user, it looks exactly the same. You're just working with a SQL interface, and however you would use MySQL, you use Vertica. But under the hood, it just goes crazy. It connects to Spark, Kafka, and ETL. Of course, because it's a database, it connects to all of the BI tools. Right? That's one thing databases do really well. And everything is typically done in SQL, but you can write user-defined functions in R, Java, and Python. So typically, data scientists that I see using Vertica are either doing SQL or R. Those are typically the two ways they like to go. And inside it, you have a lot, in addition to the standard SQL, select star from, group by, all that jazz, sum, average, you have a lot of different analytic functions that are built in too. And it works on the cloud or on-prem, and it can read and write Oracle and Parquet, and so it works well with the Hadoop environment. So here's some of the bullet points that go along with this little architecture here. Just like Spark, it can scale easily. It obviously has built-in data storage, which Spark does not have. We'll talk more about that in a second. You have really smart ways of compressing the data and optimizing it for analytics. This bullet point, you might be saying, I don't believe you yet, Josh. I'll show you some benchmarks on this one. It's not memory bound because you can tie the analytic algorithms to the data store. You don't have the out-of-memory issues, so you can spill the disk when needed. The developers can write it that way. You and me, the analysts, can really do things quickly in SQL. So if you don't know Java, Python, Scala, R, whatever, SQL, you can still do machine learning. Then this one's pretty big. Actually, these two right here are pretty big. And people don't think about it a lot, especially maybe as an analyst, we don't think about it a lot. But as you start to move up in your career to where you have to make decisions, and maybe you're already there, you have to make decisions about which tool I'm going to use, which tool is my department going to use. Things like high concurrency are huge in this space. And by that I mean, can all of you guys in this room hit the same data source and run machine learning models on it without a doubt? In Spark, if I were a system admin, I'd have to carve out a memory space for each of you. Your own little sandbox of compute and memory. In a database, you don't have to do that. The databases are kind of designed from the ground up and have lots of users. That's one of the things that databases are always judged on. How can you handle 100 users at one time hitting the same query? So that same principle applies to machine learning. Now you can have 100 different data scientists building machine learning models in a database at large scale, and the thing just goes. It handles it fine. Also, you get the enterprise stuff like security, high availability, disaster recovery, all that stuff comes along with it. Oh, and this one. I didn't have this one on, but one of my sales colleagues was looking at this and said, hey, what about support? With Vertica, you can call support. I'm like, okay, sure, you can call support. And some people really like to be able to call somebody on the phone and say, hey, it's not working, how do I do this? And so there you go. So here is a architecture slide where they both are living side by side. But this is a Hadoop example I just grabbed off the internet. Here you've got the databases, MPP, EDW, RDBMS, and well, I got a little build here. So Vertica, Greenplum, and Tisa can live either here, or they can, some of these can be installed right on HDFS as well, right on Hadoop. Now what's different about the compute engines, they are here and here. Because they can be installed right on the same hardware as the data, they need their own separate space for compute and memory, but they can also be a totally separate kind of analytical tool that sits on your laptop or wherever that points to that data. Okay, so, oh, I got messed up a little bit. All right, that's a bummer. That's what you get when you get a Microsoft presentation trying to display on a Mac. They don't get along too well. So I will have to interpret this a little bit for you, but you can see the graphs here, which is the main part. So orange is Spark and blue is Vertica. This was, just look at the last column, if there's too much data here to digest. That's 1 billion rows of data. So 10 million, 100 million, 1 billion. And each of these has 100 columns. And this was on Spark 2.0 and Vertica 8.1. So you can see down here, it didn't get messed up. This title, the title for this got messed up around. What this basically, the takeaway here is if you're running a k-means, it's going to take you a little over 2 hours to run it in Spark on 1 billion records and 7 minutes on Vertica. So as an analyst, that's a big difference, right? And then if you're coming down to, let's go over here to naive Bayes. If you divide this by 60, that's pretty much a day. That's me back in grad school hitting go and going home. So you're running a naive Bayes on Spark, 1 billion records, 100 columns, pretty much a day, and a little bit over an hour in Vertica. So there's quite a, and the reason why you get that speed improvement is mostly has to do with tying the compute to the data storage. There's tricks that developers can do when you don't have to be general across all data storage types. I'll get into a little bit of that here. Here are a few of the bullet points. Checking my time to see just a few things, a few tidbits. There's a lot more than this. But, oh, I forgot to say, up there in the corner, when we ran this benchmark, we preloaded all the data into Spark's memory, which is a big time killer. And we didn't do that for Vertica, because Vertica has the tables on disk, and it's so optimized to put it in memory, it just happens really fast. So these numbers include loading from disk to memory for Vertica, but do not include loading into memory for Spark, and sometimes that can be as much as was already there. So it could double sometimes the time that it took Spark to finish. So this is talking about the memory access. It's quick with Vertica. It also has something called Blob Data that allows you to control the resource pool, spills to disk, and you can really get down into the weeds on how you maximize parallel processing. And then our development team spends a lot of time on algorithms, on really trying, they borrow a lot from Spark. They look at the Spark open source algorithms, but they borrow from that and try to make it better if they can. Okay, so here's what it looks like. Here's some actual SQL code. This is the Iris data set. You guys familiar with Iris data set? You guys have all seen that one before. It's a very common kind of toy data set where you're not going to show speed at all, but you're just going to show functionality. So this is 7 steps to do start to finish, nothing to a model, Iris data set inside of Vertica with machine learning. So number 1, you create the table, right? So that's your standard SQL statement to create the shell of the table, no data's in it. Number 2, you're copying from a CSV file into that table, so now the table's loaded with data. Number 3, you're creating the test data. So you got 25% table sample, so we're going to create a test set and a train set. So you got 25% of the data into the test set. And then on number 4, we're selecting everything else into the train set. Okay, so you've got your test and train now for your model building. And here's the actual call for a random forest model inside of Vertica. So it's select rf underscore classifier, and then in parentheses you put all your stuff in there. And that's really all it takes to run machine learning on a table inside the database. This is the name of the model. This is the name of the table that's being sourced for the model. This is your dependent variable, and then all your independent variables. And then there's a long list of parameters that you can tune for the random forest model. That's only 2 of them there. 2 of them they haven't put into that model, in that syntax. Here's how you score the model. So now this model is built, it's stored as something called myRF model. And now here, we're going to create a new table that holds the scores. So we're going to create a table called iris predictions as select species, which was the dependent variable, comma, predict underscore RF underscore classifier. So this is a little function name. So that's the SQL call that applies the RF model to the data. And now you've got those scores. And there are lots of things like a confusion. This one's showing a confusion matrix. So there's a little, another SQL call built into Vertica called confusion matrix, and it produces something like this. So pretty much anything that you could visualize in a tabular format, Vertica's writing that type of thing into the database machine learning library so that you can just call it real quick. So like an ROC curve, right? You could visualize an ROC curve tabular, right? You can just have the table instead of the curve. So there's also an ROC function as well. How do you do that in Spark? So this is some Scala code. I'm not going to read through it all, but I've got the steps. Basically, that first block loads the libraries, save the parameters, change the column output, extract the names, and I can share this presentation with you later if you'd like to look at the code in more detail. Convert the data to a vector of features and labels. That's one of the common things you do inside of Spark, and sometimes inside of Python too. R kind of takes care of that for you. Maybe you can use a data frame. Divide data into partitions, split the data, cache it, and then create the trained test sets. Build the classifier, apply the classifier, convert the model into a text string for analyzing, make predictions, calculate accuracy, and then clear the cache. So if you notice, there are some steps like caching, creating your feature list, stuff that you have to do because you're working with raw data, that you kind of skip some of that when you're working inside of a database. The structure of a table inside the database acts like a data frame inside of R. And it takes care of, it abstracts a lot of that mess for you and makes your life a lot easier. So in the aggregate, you've got 7 lines of code in SQL and 28 lines of code in Scala, and that's just for a toy example. So this can really get pretty big with real projects. All right, I'm doing okay on time, but I think I'm going to skip this one for now. I thought I mentioned some other technologies out there that are in the distributed space that might be important here, but we can talk about this later if we want.
Don't skip it because it's kind of important when you talk about machine learning.
Which one, what part of here would you like to talk about for
The
sure?
second one. I would love to hear about cubes as well.
About which one?
Cubes.
Okay, so cubes is the idea of kind of pre-caching data. All right, that's basically what it is. It's typically thought of in the BI space, business intelligence space, where you have too much data and the underlying engine to the BI tool, which is typically a database. Sometimes the BI tools have their own engines, really their own memory. But if the underlying engine is too slow, you have to create a cube so that then the dashboards and charts can run quick. But the problem is you can only ask a question of what's in the cube. If you ask the questions outside of what's in that saved memory, you're toast. You have to rebuild the cube, and that takes all night. So with Vertica, one thing that we do in our pilots with people is we'll say, hey, throw away your cube, try your cube against our raw data and see how fast it goes. And usually we're pretty dang close or faster than their cube, and you don't have to build the cube. You can ask any question of the data that's in there. So TensorFlow is a space where you're doing deep learning, right? And I didn't consider that here. Deep learning, I'm not even sure, I haven't researched it enough. You can do other learning too. I haven't researched this enough to know how far they've gotten into the truly distributed modeling. From what I can tell so far, they're using the same algorithms that, at least some of the models using the same algorithms that are found in like R and SAS for the traditional machine learning. And deep learning is where I hear about this most of the time. But please. Okay, after this, right. Let's see. Okay, these slides got crazy. All right, yeah, this looks fun. Okay. There might be a slide coming up where I can summarize all this to us. Let's see, let's hope. Wow. That's cool. All right, let me go out of presentation mode, and that might fix it. Let's try this. And I'm not a Mac guy, so let's see. Nope. Okay. Let me do. Yeah, we'll do this slide here. Not exactly the format I had in mind originally. There's a really cool little hub and spoke picture here that turned into this somehow. This is wild. So the hub, and there was a hub, and then each of these big triangles was a little spoke out of the edges. They got turned into this somehow. That's interesting. So these are, in my experience in working with, see, this is what I get for trusting the Mac. Yeah, it's my fault, not yours, Ben, not yours. In my experience with looking at distributed machine learning and where do people go when they're making their decisions, these are the criteria by which I have found people to judge which camp do you want to go into. So there's data, and in data you have data size, data types, and data location. And then this one is organizational. So you've got how many IT and data engineers do you have? How many computer scientists do you have? How much concurrency do you need? Do you need everybody in this room hitting them all, building all at the same time, or is it just you three? That's it. You laugh. This one is model agility. So here we're talking about building models quickly. How deep can you go? I think this one was actually called model accuracy, is the title I gave to this one. How deep can you go in model variety? And the last one was deployment. So let me just step into this verbally. I can post a PDF that has this in a prettier arrangement later. First of all, for data size, obviously we're talking about large data. In my experience, the databases can handle the larger data sizes a little bit better than the compute engines. They both of them can handle the same size. The databases will go a little bit faster. Data types is better in the compute engines. So things like Spark, they can handle any data type. In a database, obviously, most of your data is going to be structured, right? It's in a relational database. It's structured rows and columns. But it can handle things like logs and semi-structured data too, but compute engines have the edge there. Data location, they're about the same. Both of them can work on the cloud, both can work on-prem, both can work on Hadoop. You got flexibility. This is where it starts to get a little bit interesting. So in your organization, in my experience, I've found that organizations that don't have a large army of data engineers really like the database option, because they don't have that army of people to stand up and maintain Spark on Hadoop or on AWS or wherever it might be. And when you and I use Spark, it's like, hey, let's just stand it up and use it, build my model, great, but we don't think about security, we don't think about concurrency, we don't think about handling memory, allocating memory, how many nodes do I need, how many computers do I need. There's lots of things that go behind the scenes that the admins and engineers need to worry about, and it's just so much easier if you're doing that on a database. Actually, I've found in my experience that going from an open source, let's say Hadoop environment, to a database, the same workload has about a third of the hardware. So it's about, you save 2/3 on the hardware by going from Spark Hadoop to something like Vertica. Computer scientists, so if you have the computer scientists, the data scientists, great. They can go into Scala, they can go into Java. If you don't, they probably know SQL, so that's an advantage there. And then I've already talked about concurrency. Databases are built for that. Model accuracy, this is the place where databases shine, but compute engines still have a say there. This is the place where compute engines shine, but databases still can play a little bit. Model agility. I have a little bit of time. So what would you guys say? I want to hear a little bit from you. What are the most important things that affect model accuracy? So think about that for a second. What affects model accuracy? And maybe if you don't respond, just think about it. So what are some just general factors, right? I mean, obviously for every case it's a little bit different. But what are some general factors that would affect whether a model is accurate or not? Any thoughts? What's that?
Feature engineering.
Feature engineering. So being able to prepare the data intelligently. Definitely. That is what is it that everyone says 80% of a data scientist's time, or 90 to 60, people give a range, is spent in data preparation? I found that to be totally the case, usually more like 90. It's just a lot of time spent data preparation. So being able to do that quickly is important. In my experience, doing that with SQL is a whole heck of a lot easier than doing it with something like Scala. You can just go fast, prepare, new features, combine them, do cool things, and now, so data preparation goes a little faster. So that was one of my, I had in my mind. Any others?
Amount of data.
Amount of data, that's definitely one. Now, I've read scholarly articles on how much the number of rows affects accuracy, and usually the graphs, if it goes, say number of rows along the x-axis and accuracy from small to big along the y-axis, your graph goes something like this. Right? It starts to level off, but it goes up slightly. So you get a lot of improvement real early with more rows, but then that tapers off. But it definitely does add value. And there's probably one other, but maybe some others. I'm thinking of one of them. There's probably more than that.
Velocity.
Velocity.
Your data changes fast.
Yeah, that wasn't what I had in mind, but that's one that I thought of before. Data variety, right? Is kind of, well, no, you're saying velocity. So velocity could be variety in that you add a new data source, you add an IoT data source to your model. But also, if you do, now that is going to change, and your accuracy might have been great today, but it's going to suck tomorrow.
Velocity is also more of a, you have to rebuild your model quite often.
Right. And you might need to rebuild the model quite often, which is true, and you might need to put in automatic mechanisms to check model health. And I know some pretty cool startups in the Valley right now that are built just around model health management. I think it's going to be something that's going to happen a lot in the future. The other one that I was thinking of was, it just escaped me, model variety, the type of algorithm, right? What type of algorithm are you going to use? That's probably a big factor in model accuracy. So out of those, the compute engines like Spark nail the model variety. You can build all different types of models. You can build ensemble. You can get really tricky with the hyperparameters. Compute engines are great. The databases they're still working on. They have good libraries, but they're not at the level of Spark yet, as far as the library goes. But model agility is really, databases are really good at that. So you get a little bit of both there. And then finally, in deployment, you can deploy anything if you have the right resources, but if you're any type of resource-constrained environment, then the databases just deploy so much easier. Let's see how my concluding slides look good or not. We've got to wait for this to build. See, there's the spoke. That was on the spoke. I don't know where the rest of that came from. All right, so second to last slide. Key takeaways. Most organizations have both data marts and compute engines already. So evaluate what you need, what your analytic needs are, and put the right workload on the right tool. And if you haven't ever considered data marts, which by the show of hands at the beginning, most of you probably haven't because you didn't know about them, I think they're a little bit of a hidden gem out in the data science space. There's definitely, Spark's not going away, it's a strong player, H2O's not going away, Revolution's not going away, but these data marts are really accelerating in the space for a number of reasons that we talked about today. And some of those are labeled out here on this slide as kind of a final takeaway. So I'll let you look at that while I say thanks and then take questions.
Thanks so much for the great talk. We have time for questions. People want to raise their hand. We can pass around the microphone. Perfect.
Yeah, I think one consideration I saw in there that I didn't see on there was pricing, I guess, and where does that? I was wondering where that fit in with all the others. The other question was on the performance graphs. What caused the elbow between like 100 million and a billion rows? Like there was the performance gap was tiny and then it explodes. Like what specifically is it that like causes that runtime to just skyrocket on Spark?
Yeah,
like,
great.
Above 100 million.
I probably would have hit pricing because I had it in there if my slides didn't go nuts on me. The 1/3 of the hardware was part of that conversation. There's also software costs and support costs, the three things I considered. Software costs are obviously going to be more for a database because the three databases I mentioned, because they're all proprietary databases, whereas Spark, H2O, and Revolution, I'm not sure what Revolution's doing now, they're part of Microsoft. Spark and H2O are open source, so zero software costs there. But on the support costs, things start to balance back out. With support, you do pay some support with those three databases, but your support costs are much higher for the open source. I mean, there are companies like Hortonworks who that's their whole revenue flow is support, right? They don't sell any software really, it's all just support. So the open source compute environments have a lot more in support, so support and software tend to average out. The other question, what makes the bin? The elbow?
Yeah,
Yeah.
the performance, like why is it like really close at 100 and like way farther at really...
Yeah, well, I mean, if you think about the idea that's been around for centuries now of statistical sampling, right? So my master's degree is in statistics, and academic statisticians will argue sometimes, well, almost all the time to their detriment, that machine learning is dumb and we need to stick with regular old statistics. You hear that too much in academia. It's because they feel like a lot of questions can be answered with small data sizes, small sample sizes. And depends on the problem, and to some point, they're right, but there comes a point of diminishing returns where you've got enough data to capture the pattern, and any more data is going to add to that pattern incrementally.
The other graphs.
The other graphs.
Yeah, the runtime.
Oh, sorry, I thought you meant my air graph with my arm. No, the runtime. So tell me the question again, please.
So there's like the gap between Spark
Oh, yeah.
is small at 100 million.
Yeah.
And like explosive
Memory.
at a billion. Yeah, what causes
Memory.
that? Yeah.
Memory, yeah.
So it's just the memory.
Yeah, Spark, everything has to fit in memory. And when it doesn't fit in memory, you have to do trade-offs and swap outs, and that gets really expensive computation. So with the database, because it's tied to storage, if it runs out of memory, it can spill the disk smartly right back into that table structure. Everything stays in the table structure the whole time. So you don't lose the table structure. Whereas with Spark and H2O, they have to talk back and forth between disk and memory a lot. So it's not being able to optimize for the storage layer. Yeah. Questions?
Hi there. You made a point about programmer productivity being higher with a solution like Vertica by virtue of the fact that you have a declarative SQL-like language or SQL itself compared to a control flow-based one. With Spark being layered on top of, or with SQL being layered on top of Spark through either the CalSci project or Spark SQL, isn't that advantage essentially negated?
It's catchy. It's narrow. It's not negated. If you look at the TPC DS and the other TPC benchmarks, the last I checked, I know that they're always getting better, but things like Impala, Hive, Spark SQL still cannot do all, let's say, 99 of the TPC DS benchmarks. And maybe there's some new studies out that are contrary to what I just said there. But last time I checked, a year or two ago, they were still working on it. And the databases that have full ANSI SQL support is just more familiar to the average SQL programmer. They can just go and do it. Hive pool is a little bit different. Spark SQL is better at being more of a true SQL language, but with things like Impala, sometimes you have to actually call out what partition you're using on HDFS. That's just a little bit cumbersome. You want to just let the underlying system take care of that work for you. So it definitely is narrow, but in my opinion, there's still a gap.
I have two questions. First is, which is the most ethical architecture to deploy? And the second is, two of the interesting deployments of this distributed ML has been in the gaming space and healthcare. So the protein folding, and then recently in Dallas, using Minecraft, a mod for Minecraft. Can you, given your perspective, just share some of the cool stuff you've heard about the other approaches to massive ML?
Sure, yeah. First of all, on most ethical, I think I could argue both sides of that, but one thing that most people think open source ethical, proprietary not ethical, bad. One thing to keep in mind, open source, especially if you're talking about cloud-based solutions, they want to lock you in just like anybody. And Cloudera wants to lock you into Parquet. Hortonworks wants to lock you into Orc. Amazon wants to lock you into AWS, Microsoft wants to lock you into Azure. If you have one of those databases, because they are not tied, because they have their own storage layer, and they can install in any of those places, you're not tied to any of those. So you are now free to move cloud to cloud. You're now free to move data to Orc to Parquet to CSV to anything you want. So just one aspect of the ethical question most people don't think of. To your other point, I have a brother-in-law who is a biomedical engineer at the University of Virginia. And they are doing super cool stuff with machine learning. Most of it right over my head. I can't really speak to all the things that they're doing, but there's definitely, it's really a growing space. So I've been doing this for 17 years. I've been calling myself a data scientist for 7, right? I used to be a statistician. Now, hey, now I'm a data scientist. It's good to have your life. I'm doing the same thing. I found that the shift in the industry is going a little bit away from people like me who came at it from the stats angle, and starting a little bit more now with computer science. So I think there's a little bit more of the computer science bent to it these days than there was a decade ago. And the computer scientists are having to learn statistics so they don't do something crazy and mess it up. And rather than it used to be the statisticians were trying to learn how to program. So it's a little bit, the pendulum's swinging a little bit. I think there's a good happy medium that eventually, I think, we can meet. But and then your other question was on gaming. Yeah, I mean, Zynga is one of Vertica's first and our favorite customers. I don't remember you guys might remember the stats on it, but they increased their Vertica footprint something crazy like 20 times in 2 years. That's how much data, once they started going, that's how fast this thing grew. And there's just so much data to collect off in the gaming industry that there's unlimited things they can do, and I don't know how much of it is technical, but they can do a lot.
So what kind of database are we using? And let's say I have a Postgres. Would I be able to integrate with any of these, or is this completely separate?
Yeah, some of the technology it's not Postgres. It's similar to Postgres in some ways. So it's all 3 of those databases that I had mentioned are all columnar databases. So they're built for analytics, built for fast query of limited columns. So columnar means instead of looking row by row, I'm looking column by column at my file. So the files are saved in columns on disk. Transactional data systems where you just load, you want to save that stuff in rows because you're calling up rows at a time. But when you're doing analytics, like that random forest model that you saw, you're only calling 5 to 10 to 20 to 50 columns out of thousands. So you just want to right away you throw away all the other files. That's one reason why they're so much faster than the other stuff. But no, those are columnar MVP databases, so it's similar to Postgres, but a little bit different.
Question, right? So just to follow up on the question earlier, you said, for example, okay. All right, so you can one of the slides said you can write like your UES and Python,
Yeah.
for example. So coming from, let's say, Python background, let's say you do scalar and 3D machine learning, it seems like you're first of all, you're locked into the functions that the database provides to do machine learning.
Right.
We haven't really looked at what it takes to create your own functions.
Right.
Right. If you wanted to, I mean, how would you go about that? Can you integrate with your existing, well, let's say, for lack of a better word, knowledge base of skills in the machine learning space?
No, that's a great question. So you have an existing knowledge base of skills, R, Python, whatever it might be, and this stuff that runs in databases is wicked cool and wicked fast. But what if I really want to run my special algorithm and it's not in your database? You can with the UDFs. The difference being they're going to run slower. But what they do is when you run that user-defined function that's based on, let's say, R, you can say partition that function over all my nodes. And it will split that function up and put one copy on every node, and then Vertica comes with an R instance already installed and a Python instance already installed. And it will automatically take care of partitioning or distributing that algorithm across every node. And then, but the key is it won't do the reduce step, because that's a whole nother ballgame. That's where companies like Revolution started, because they built the reduce step for R. Vertica is building the reduce step for Vertica. Spark built the reduce step for Spark. So it will run a random forest in every node, but then you're going to get, if you have 3 nodes, you get 3 random forests. But if there's a data preparation routine that you really like, it'll run on every node really fast, distributed, and now all your data is prepared. You have a new feature. Does that answer your question at all?
Yeah, I mean, what would be great, and what I'm wondering is there a way to just sort of a separate question, to integrate Vertica into your own, let's say, Python workflow where you call Vertica and push a function and then get results back?
Yep. Yeah, I do that all the time. I have my R workflow. I usually work in R. So I have my R workflow. There's a simple JDBC connection. I say, push the SQL to Vertica, build my random forest model. It'll build it and give me back the results. They're really small. And also, you can run any type of modeling from R in Vertica as well. It'll just run on one node. You just have to tell it, hey, only run this on one node, because I don't want 4 models on all 4 nodes. I just want one model. So it'll run a little bit slower because it brings all the data to one node, but it'll do it for you. And you can integrate R into your Vertica workflow, or you can integrate Vertica into your R workflow. Either way.